and welcome to today's session from Data Zen community. Our guest today is Rahul. He will share his experience of building high performance data pipelines with Go and Kubernetes. Important thing that during the session you will be able to see demo and maybe even try to set up these modern tools locally or in your cluster. Yeah, also don't forget to ask your questions in the chat. They all will be discussed during QA part. So without any additional words, yeah, Rahul, floor is yours.
Yeah, thank you, Alexander. So, hi everyone, I'm Rahul Sid Patil, and today I'll be walking you through a developer's practical approach to building high performance data pipelines using Go and Kubernetes. This session is specially designed for beginner level backend and cloud engineers. So don't worry if you're new to Go, Kafka, or Kubernetes. We will walk through everything step by step. The entire demo is based on real world experimentation, and everything I show today is 100% reproducible through a public GitHub repository that I will share at the end. Whether you are exploring how real-time ingestion works, curious about Go for backend systems, or trying to scale your services with Kubernetes, you are in the right place today. A little bit about me. I'm Rahul Sid Patel, and I currently work as a lead software engineer at EPAM Systems. I also lead the Golang community at EPAM India, where I mentor engineers and guide adoption of Go for cloud native projects. With over 12 years of experience in backend engineering, I specialize in building distributed systems using Golang, Kubernetes, Kafka, and other cloud native technologies. I'm the author of upcoming book Let Us Go Volume 1, a complete beginner's guide to Golang programming and development. This is designed to help developers learn Go by building real tools, not just reading syntax. I regularly write technical blogs on LinkedIn and Medium where I share insights on Go, Kubernetes, and architecture patterns. I also run a YouTube channel called Cloud Native Developers Forum, CNDF, where I publish hands on demos, tutorials, and explainers for beginners about cloud native applications and AI. If any of this sounds interesting, feel free to connect on LinkedIn or drop me an email at golangda@gmail.com. I would love to hear from you guys. Let us start today's session with a quick real world story. This is a true story. Segment, which is now part of Twilio, a major player in customer data infrastructure, used to handle their real time event routing with Python. But as their data traffic grew, they hit a wall. High CPU usage, memory bloat, latency spikes, and growing server costs and whatnot. They decided to rewrite the critical parts in Go, and the payoff was massive. CPU usage dropped from 90% to 30%. Memory usage went down from 1.5 GB to just 200 MB. Latency improved 5 times, and they needed far fewer servers. The result, a faster, leaner, and more scalable pipeline. Now, how can we build something like that? Yes, we are going to answer this question today. But first, let us understand what a data pipeline is. A data pipeline is a system that ingests, processes, transforms, stores, and serves data. It typically has four stages: data ingestion, which collect where it collects data from different sources like APIs, files, or databases. Processing and transformation, cleaning and shaping the data, maybe removing duplicates, changing formats, or applying business rules. Storage, storing the processed data in databases or cloud storage systems. Serving and visualization, making data accessible to dashboards, analytics tools, and downstream services. A well-designed pipeline should be scalable, resilient, and fault tolerant. But even that's not enough in today's world. your data pipeline has to be high performance one. So next, let's talk about why we need high performance data pipelines in the first place. So far, we have looked at what a data pipeline is, but here is a real reason we care about performance. Today's users expect instant feedback, real-time analytics, and seamless experiences. Whether it is a financial transaction, a user click, or a sensor event, the pipeline must handle it fast, reliably, and at scale. That's why modern pipelines must be built for real-time insights so decisions can be made instantly, scalability so the system grows with your data, reliability so it never breaks under pressure, cost efficiency because performance shouldn't drain your cloud budget, and ultimately a better user experience. Achieving this isn't a magic, it is about making the right technology choices. So let us look at the tech stack that powers our high performance data pipeline. Now that we know why high performance data pipelines matter, let me walk you through the tech stack we are using to build one. At the heart of it is Go, which is fast, lightweight, and handles concurrency like a pro. It is perfect for building real-time data processing systems. Kafka is our event streaming backbone. It helps us buffer and decouple producers and consumers with durability and scale. We use MongoDB as our storage layer. It is a flexible, schema-less NoSQL database that works great for rapid inserts. And finally, everything runs on Kubernetes, which helps us orchestrate, deploy, and auto scale the pipeline components as needed. This stack is battle tested and gives us everything we need to build a pipeline that is fast, scalable, and production ready. So, pipeline architecture. This diagram here shows the overall architecture of our demo pipeline in action. It starts with a dummy data generator. This simulates a live stream of events similar to what you would get from user activity, IoT sensors, or logs. These events are pushed into Kafka topic, which helps us decouple the producer and consumer, ensuring durability and real-time delivery. Our ETL app, written in Go, continuously consumes messages from Kafka, transforms them, and pushes them into MongoDB for storage. This entire flow is deployed inside a Kubernetes cluster, which handles deployment, restarts, auto scaling, and failover for us. This is the core pipeline that we will be building. Next, I will walk you through the step-by-step plan to set this up on your own local machine. So here is a step-by-step plan to build and test our pipeline from scratch. We will start by setting up Minikube, which gives us lightweight Kubernetes cluster running locally. Then we will deploy a Kafka cluster inside that Minikube environment using Helm or custom manifests. After that, we will spin up MongoDB, which will act as our sync database. Next, we will deploy a dummy data generator, which is a Kafka producer that continuously pushes test data into the topic. Then comes our ETL application, again built in Go. This will consume Kafka events and write them into MongoDB. For advanced setups, we will add an HPA, that is horizontal pod autoscaler, to show dynamic scaling based on memory utilization. And finally, we will benchmark the whole system to observe throughput, latency, and resource usage. Each step is modular, so you can test and improve components individually. Let's begin with step one, setting up Minikube, which gives us a local Kubernetes environment for testing our pipeline end to end. Rather than manually executing each command, we have added makefile targets to streamline the process. First, we run make Minikube start. This launches Minikube with 4 CPUs, 8 GB RAM, and Kubernetes version 1.33.1. Next, we use make Minikube verify. to confirm the version and check the cluster is up. Then we use make Kubernetes check. It runs a set of kubectl commands to validate cluster info, services, namespaces, and nodes. Optionally, we can run a make minikube dashboard to enable and launch the Kubernetes dashboard in your local browser. This gives us clean and verifiable Kubernetes environment to deploy Kafka, MongoDB, and our applications, all with just a few commands. Now that our Kubernetes cluster is up and running, let us deploy Kafka in craft mode. That is Kafka without Zookeeper. Instead of instead of running raw Helm install commands manually, we have wrapped everything in a makefile target for consistency and repeatability. Here is what happens under the hood. First, we add and update Bitnami Helm repo. Then we create a dedicated namespace for Kafka cluster. And finally, we install Kafka using predefined values.yaml file that includes Kafka craft enabled equal to true, tuning for persistence, resource limits, and service exposures. So with just make install Kafka cluster, you will have a fully configured Kafka cluster up and running in craft mode inside your Minikube environment. With Kafka in place, we now deploy our MongoDB database, which will serve as storage layer for our transform data. We are using a single pod setup, lightweight and perfect for testing throughput, latency, and end-to-end flow. The entire deployment is managed using makefile targets. Make Mongo install triggers 3 steps. Install applies a simple mongodb.yaml file that defines a stateful set and a service. Test verifies pod readiness and connectivity using MongoSH. initdb bootstraps an initial database and collection by copying, executing a JavaScript init script inside the pod. Now that our storage and Kafka layers are ready, it is time to kickstart the data flow. We do this by deploying a dummy data generator, a Kafka producer written in Go. It continuously sends JSON formatted messages to a Kafka topic called test data, mimicking the behavior of real-time data stream. The deployment process is again wrapped into clean makefile target, make dummy data generator install. Behind the scenes, it builds a Docker image, loads it into Minikube environment, deploys it as stateful set using Kubernetes YAML, verifies pod readiness and container logs, and even checks Kafka connectivity using CLI tools within the pod. You can also tune the message rate via configurable sleep interval in the code. This makes it easy to simulate low or high load for benchmarking. Now that the Kafka topic is filling up with data, our ETL application steps in to complete the pipeline. This is a Go-based Kafka consumer that listens to messages from the test data topic, converts them into MongoDB's bson.m format, and inserts them into a collection named etl_db.data. As with other components, the deployment is automated via make etl consumer install. Behind the scenes, this builds and loads the Docker image into Minikube, applies Kubernetes YAMLs for the deployment, and MongoDB credentials, and verifies pod readiness. The ETL application is designed with concurrency in mind. It can efficiently process multiple messages using Go routines. And here is the best part. We have made it auto-scalable. As data traffic increases, we need our ETL app to scale, but doing it manually every time defeats the purpose of cloud native automation. That is where Kubernetes HPA or horizontal pod autoscaler comes in. We have enabled HPA for the ETL app to scale automatically based on memory usage. When load is low, it runs with just one replica. When memory crosses the configured threshold, let's say 60 or 70%, Kubernetes automatically spawns more pods, up to 5 in our case. This makes the system responsive to workload spikes, such as when we scale up the dummy data generator or push bursts of traffic into Kafka. The autoscaler is deployed using makefile target make ETL deploy HPA. With this, the pipeline becomes self-healing and elastic, which are which are key traits of modern production-ready systems. With all components deployed and auto-scaling in place, it is time to test the pipeline under load and see how well it performs in real time. We ran a custom benchmarking script, run benchmark.sh. It collects metrics like Kafka messages produced, MongoDB documents inserted, CPU and memory usage across pods every 5 seconds. For this run, 1,000 messages were sent to Kafka. All 1,000 were inserted into MongoDB. There were no drops, and MongoDB kept up with the producer. The ETL app's average CPU usage was just around 160 millicores, showing that the app remained resource efficient even during load. This proves the pipeline is stable, auto-scalable, and production ready, even in constrained Minikube environment. Let us see all of this in action in the next demo video. For convenience, I have recorded all the steps we executed. In the first step, we start Minikube, as I mentioned. Then we verify whether Minikube was pro properly started or not. Then we use Kubernetes check make target to check all the Kubernetes pods are up and running and in given namespace. We launch a Minikube Kubernetes dashboard for observability. It comes handy. You can launch it in your local browser. Right now, there are no workloads. Now we install Kafka in craft mode using make Kafka install target. It will install Kafka from Bitnami charts and will verify the Kafka pod statuses and also check whether it is capable of consuming uh, the messages or not. Once this is completed, we can see the Kafka workloads in our Kubernetes dashboard in namespace called Kafka. We install MongoDB now. In our Kubernetes dashboard, we can see the MongoDB pod is running. We check that there is only one dummy message in MongoDB which we created during initdb step. That means the messages are not yet being pushed to MongoDB because there is no ETL consumer app. We install the dummy data generator app. We built it from local Docker file and deploy it in Kubernetes cluster as a stateful set. The installed script itself checks its status. We can see that it has started producing the messages. You can see dummy data producer pod is deployed in the same namespace. For the convenience of this demo, I have deployed all the workloads in the same namespace, Kafka. In production environment, generally these workloads are deployed in different namespaces to achieve compartmentalization and security. You can see the logs. It has started generating the messages. These messages are still not being inserted into MongoDB because there is no consumer app running. We're now installing the consumer app and verifying its status as well in the same make target. It has started consuming the messages. You can see we have deployed ETL consumer. Yes, ETL consumer pod is running, and it has started consuming and inserting the messages into MongoDB. Now in MongoDB, you can see an array of messages being inserted by ETL consumer app. Now let us see how HPA works. To demonstrate the HPA in action, we have made some hacks here. Right now we have kept resource utilization at 70%, average resource utilization threshold. Unless 70% memory is being utilized, the autoscaler will not trigger. But for this demo, it is very hard to push to 70% memory. I just reduce the threshold to 2% so that autoscaler will kick in. Autoscaler has kicked in because the memory usage is above 2% and it has scaled up number of pods, autoscaler pods. I again change it to 70% to demonstrate the scale down. It The scale down has triggered again, and the number of pods are scaling down to 1. So that's it. That was our data pipeline in action. Before we move into resources and FAQs, let me quickly recap what we have built together. First, a fully working Go-based data pipeline running entirely on Kubernetes with Kafka and MongoDB. The architecture is clean, scalable, and modular, built using small Go services for real-time ingestion and transformation. We demonstrated auto-scaling with HPA, proving that the ETL app can handle increased workload automatically. Most importantly, this is not just a demo. It's a framework you can extend into real-world pipeline, whether you are processing logs, user actions, IoT signals, or events from microservices. Up next, I will share some useful links and materials that will help you explore or build on this project further. And then we will wrap up with a few common FAQs I usually get around this topic. These are some useful material links. If you'd like to dive deeper or replicate what we have built today, here are some helpful resources. The full source code and setup instructions are on GitHub. Everything from manifest to make files and benchmark scripts you can find in a GitHub repo called rahul.patil/go Kubernetes data pipeline. To understand the internals of Kafka's craft mode, the official Kafka documentation is a great starting point. If you are new to Kubernetes, their docs are incredibly comprehensive, especially around workloads, services, and autoscaling. For Go developers, I highly recommend the Active Go guide on concurrency. It aligns perfectly with how we built our ETL app. And finally, the MongoDB Kubernetes operator docs are great if you plan to scale beyond single pods or add replication. I'll leave these links up for a second and then we will head into the final section. Some frequently asked questions I get when presenting this pipeline. I usually get a few common questions after this session, so let me address some of them upfront. Why Kubernetes? Why not just run Docker containers directly? It's a great question. The answer is orchestration, autoscaling, and resilience. Kubernetes allows us to manage distributed components like Kafka, MongoDB, and Go services efficiently. With features like automatic restarts, rolling updates, horizontal pod autoscaling, built-in monitoring, and resource allocation, it's a perfect match for building real-world pipelines that need to scale, heal, and stay online. What are the system requirements to run this locally? You don't need a full-blown cloud setup to try this out. A decent laptop with 16 GB RAM, 4-core CPU, Docker, and Minikube installed is more than enough to get this pipeline up and running locally for testing, development, and demos. Let's finish up with two more questions I often get after this session. Uh, is this pipeline production ready? The architecture is definitely production extensible, but for real world use, you'll want to add proper logging, error handling and retries, authentication and access control, CI/CD pipelines for deployment, observability with tools like Prometheus, Grafana, or OpenTelemetry. In other words, the core skeleton is ready, but real world polish needs operational hardening. Can I run this on public cloud? Absolutely. You can deploy the same stack on AWS with EKS, GCP with GKE, or Azure with AKS. In fact, that's the logical next step once you validate it locally. And with that, I'd like to thank you all again for your attention. Let us open up for a live Q&A.
Thank you very much, Rahul. Yeah, very interesting presentation and demo. Now
Thank you.
let's move to questions. We have them several. Yeah, why have you chosen Go? Why not Python or Java or something else?
I think I answered this in first couple of slides because of its
Uh-huh.
performance, ease,
Oh,
and scalability. Yeah.
mhm. Uh, yeah, also one more question about data quality of this data pipeline. So is there any data quality implemented or how it can be implemented?
So to implement data quality, there are several ways. With this pipeline, I'm just using dummy data and transforming it to MongoDB JSON format. I've not implemented uh, data cleaning or data hardening, but that can be easily done with performance, with high performance, with Go because Go supports high level of concurrency. Yes.
So it means that this data quality will be implemented, data quality checks will be implemented with Go.
Yeah, we can do that. Yes.
Mhm.
Even in today's world, if we go for further, like I was working on Gen AI RAG development with Go. So there we can use a mix of some LLMs and RAG is written in Go to achieve this kind of additional processing at scale and with performance. Yes.
Mhm. And yeah, about so uh, could you suggest maybe some data report or data visualization tools or maybe additional Docker images, like in that case, that can be
Yeah.
used to extend this platform?
Yes. Yes. Definitely. Grafana is very popular for visualization.
Mhm.
You can use OpenTelemetry, and there are a number of third-party tools as well. I will push some of the Docker files or links to the GitHub repo later.
So it means that, for example, this Grafana will just pull data from MongoDB and visualize some or like any data can be visualized from MongoDB, or it can
Yeah.
be some from
Yeah.
Kafka.
No, no, no. That's a very interesting question. Actually, in actual production environment, people generally again run one more data pipeline which pulls data from MongoDB and transforms it into different views, uh, push them into Grafana ready databases like Redshift, and they create dashboards of their choices. So there are a number of possibilities with this.
Mm-hmm. And yeah, I think we've covered all questions. Yeah, I don't see any additional questions in the chat. Yeah, thank you very much, Rahul, for this presentation. Um, yeah, I think we will share all the links that Rahul uh, has shared with us during this talk. So in the email. Yeah, thank you very much. Thank you, Rahul.
Yeah, thank you. Just
Yep.
one more announcement I want to make. The GitHub repo I have built, it is still work in progress. I will actively seek contributors to take this to maturity. Like we can extend this to add observability. We can extend this to add more components into our pipeline. We can create Kubernetes CRD triggered pipelines as well. So there are a number of possibilities. So whoever is interested, please reach out to me. We can take this project further.
Yeah, great. It's a great opportunity to contribute and do something interesting. Okay,
Yeah.
perfect. Yeah, thank you very much. Yeah, if you like this talk, or if you don't like, yeah, please give Rahul a badge and trade this talk on the event page. And all the recording and presentation file will be shared later and available on the event page. So thank you very much. Have a nice day. Bye.
Thank you all. Bye.